Hello. In this video I'm going to show you how to solve the truss questions using the cut approach, meaning that we have a truss like this, we are applying some external loads, and we are going to find the internal forces in some of the links. For example, here we may look for the forces in BC, CG, and GF. The idea here is that we don't need to go joint by joint to reach the links, and the truss could be very long, and reaching to the middle of that could be a very time consuming approach. And if we are looking for something in the middle, we don't need to go to all the joints to reach to that, and we can just cut that and find the unknowns. But here is the question is that where we can cut, and how many links we can cut, and where we cannot cut, and these are the questions that I'm trying to answer in this video. The idea is based on the equations that we have. Actually, what we have is three equations for the planar static equilibriums, including sigma of x equal to 0, and sigma of y equal to 0, and sigma m around any point equal to 0. As you can see, we have three equations here, and the cut should be cut. The cut should be like cutting three links, meaning that because we have three equations here, we can have only three unknowns, and the cut should be going. The line of the cut should go through only three links, meaning that if we have four, we cannot solve that. In some problems like this, it is possible to do a cut and have only three unknowns, and by doing that we can solve the problem. As you can see, for this one, we don't need to do the free body diagram of the whole system, meaning that we don't need the reaction forces, and we can consider a free body diagram for the left part. If we do this and put the reaction forces as the unknowns, what we would have is what we have here, meaning that I'm cutting three links, I'm putting three unknowns over there, and then write down the equations and solve this. And for solving this guy, we can use these three equations, and by doing that we can find the unknowns. And by finding these unknowns, we can find some other unknowns as well, meaning that, for example, if you are here, by doing this you can find two unknowns, and then you can get back to the joint approach which was presented in the previous video and find these two, meaning that after doing the cuts you may use the joint approach for some parts like this, or like this. But here we cannot do that, because if you solve this, we get three forces, and as we discussed before, for each joint you can have two unknowns at most, and we can solve this but not this, meaning that after this cut you can do this joint and then go to this joint. And the thing that we need to be careful about is the directions of the forces. Here it's completely arbitrary, you can put whatever direction that you like, but when you are cutting through something like this, and you put the force of BC like this on the left part, you need to put exactly the same force, meaning that the same magnitude, but with reverse direction on the other side, meaning that this would be here. And whenever you solve this you find a value for this, you put it here, and you can go through the rest of the truss. And as you can see, for example, if CF is asked, you cannot solve it directly. You need to do a cut and then go through this joint, meaning that you found these two and you can do this joint because you have two unknowns. This is the general approach we are using for doing the cuts and using the equations that we have. And the idea here is that matching the number of unknowns and the number of equations, and we can go through multiple examples to see how that works. One of the main questions that we are facing with is that where to start is, as we discussed before, the first step in solving the trusses is finding the zero force members, and then after that it could be free body diagram of the whole system. But if we are going through the cuts, it's not always the case. And then writing down the equations. Here I have one example on the left and one example on the right, and to show you where we need the free body diagram of the whole system and where we don't need that. Let's assume that you are asked to find the reaction, you are asked to find the internal forces in all the links here and here. As you can see here, if we do the free body diagram of the whole system, what you get is like this. You would have a y over here, you would have a x over here, you would have by and bx, and that means that you would have four unknowns over here. And this is not working, meaning that if you write down the equations for the whole system, you would have three equations, and three equations is not enough for finding four unknowns. And you are asked to find the internal forces. Here you don't need to do this, meaning that we don't need to do free body diagram of the whole system. You can go through these links by doing cuts from the top to the bottom, meaning that if I do a cut over here, what I get is like this: 1, 2, 3 unknowns, and I can do this without having the reaction forces and the ground forces. However, in an example like this, you cannot go through that without finding the reaction forces, meaning that here you can do the cut, you can find three links and three unknowns and write down the equation for this part, do the free body diagram of the system for this part, and then write down the equations, find unknowns. But here you cannot do that. Why is that? Because if you cut somewhere like this, for example, if you do a cut here, let me show you what is that cut. It's like this. You would have two unknowns here and two unknowns here. You cannot find your answer. And here the same. You cannot do a cut without having the reaction forces. For example, if I do a cut over here, that would be like this. And if you don't have this, you cannot find these three unknowns. In these cases, you need to do the free body diagram of the whole system, and it is possible to find the reactions, meaning that if you put a y and a x over here and dy over here, you would have three unknowns, and you can solve this finding the reaction forces and then start to cutting, or then start to select where to cut to find the unknowns. For example, if you have dy over here, you do a cut over here and you can find the unknowns in the middle, or you can do a cut like this, or you can do a joint like this. and by doing those things we can solve this problem. Okay, let's consider the difference. What is the difference between this problem and this problem? In this problem you have two fixed joints, each one of them is adding two unknowns to the system. It is impossible to do the free body diagram of the whole system. You can do the free body diagram, but you cannot solve the whole system directly. However, here we have a joint, a pin, which is fixed to the ground, and a roller. That's the main difference between these two kind of problems. And here you need to do the free body diagram at first, and then solve the free body diagram of the whole system to find the reactions, and then you can start cutting. But here you cannot do that, and you start from cutting, from where it is possible to cut and it is possible to solve the problem. Okay, let's get started and do some examples together. Here I have a question that is asking me to find internal forces in some of the members like BC, CF and FE. And the thing here, sometimes they are asking you to find all the forces of all members. In those cases there is no priority for cuttings, but when they are asking about some of the members, it is good to do the cuts through the links which are unknown, meaning that I do a cut that maximizes the number of unknowns. Here I'm looking for BC, CF and FE. It is clear that I need to do a cut over here, and this is a kind of problem that we cannot solve the reaction forces because we have two pins here and four unknowns, and it is impossible. But we can do a cut like this over here, and that means that it is possible to solve this because we have only three unknowns over here, and if I do the free body diagram of this, that would be possible to solve this. Okay, let's get started and solve this one together. I have a link like this. I have 800 newtons over here. I have a link over here, another one. This is E, this is D, and this is C, and I'm applying 600 downward over here. I put my unknowns like this. I put this guy like this and name it F of FC, and I put this guy like this, and that would be F EF, and this guy like this, and F BC. And start to write down the equations. The main idea here is that we have three unknowns and we can use our three equations, but where to get a start is the question. For example, we start from sigma of x equal to 0, sigma of y equal to 0, and sigma around any point equal to 0. The idea here is that we need to get a start with sigma m. It's make the problem much easier, and the point we take the moment around the point, which is making reducing the number of unknowns. For example, if you take the moment around point C, two of them would be deleted automatically because they don't have any arm around point C, and we can find this. Okay, then let's get started with sigma m around point C. If we do that, the only force that is making moment around the point C, and let's assume that the counterclockwise direction is the positive direction of the moment. The only point which is making moment around point C is 800, and also we have FEF which is making the other moment. If I do that, I would have minus 800 times 1, which is the arm of that, and we have a force over here that would be plus FEF times 1 as well, because the arm of that is also 1, equal to 0, and we can find FEF as 800. Okay, right now you can do sigma fx, sigma fy to find the other unknowns. If I look at this one, I prefer to start with sigma fy. And why is that? Because I have two known forces in that direction. These guys are not contributing in that direction, and the only force which is contributing in that direction is FC, and meaning that I can do sigma fy equal to 0 and find the equations like this. I have minus 800 and minus 600 and plus FC. Let's consider this triangle and name it theta. That would be sine of theta equal to 0. And we know sine of theta, actually we have a triangle like this. This is 1, this is 1, this would be a square root of 2, and sine of theta in this case is 1 over a square root of 2. And if you replace these things, FC would be 1400 over sine of theta, which would be times square root of 2. And right now I have two forces, and I can write down sigma fx. The thing here is that we are starting from sigma m because we can find only one unknown directly using that. And the same thing for sigma fy, because one unknown shows up in that. And then sigma fx. This way you don't deal with like two equations, two unknowns, or three equations, three unknowns, and that would be much easier for you to solve this way. Sigma fx equal to 0, what you would have is like this. It's like I have FBC minus FFC cos theta, and minus FEF equal to 0. And if we do this thing together, what I would have, just move it here, what I would have is like this. I would have FBC as the unknown, and FFC, I have the value cos theta, like sine theta is 1 over square root of 2. That would be minus 1400, and the EF, I have the value for that minus 800 equal to 0, meaning that FBC would be 2200 newtons. Okay, as you can see, we do the cut. We have three unknowns. It's important to start with. It is possible to do these things all together and do the sigma around any arbitrary point, but you can start from the point that gives you one unknown for each equation. Find that and then go to the other ones and go step by step. As you can see in the last one, we have just one unknown. This is the art of selecting the point that you are taking the moment around, and also the equations that in the order of equations, meaning that after sigma m I start with sigma fy and sigma fx. This is one point. The other point is the direction of these ways. As you can see, we got positive values, meaning that all the directions have been selected correctly. Why is that? It is not necessarily the case, and it is not it's not obligatory to find the direction of these guys correctly at the beginning, meaning that it can be found, you can put any arbitrary direction for these forces, but in many cases it is possible to put the correct directions. I just raised the arrow directions, and let's get back and try to find the rational directions for these guys. I have three lines over here and two forces over here. I would say you can put whatever directions for these guys. Whenever you solve this, you get some values. If the value is positive, meaning that the direction is correctly selected. If it is negative, you change the direction. That's the idea here, okay? But it is possible to put the directions to get the positive values. How is that? Let's assume this as a part which is in static equilibrium condition. If you consider this one, I would say these two forces are pulling down this structure. These guys are horizontal. The only guy which is preventing this motion is this. Meaning that you need to put that direction like this. This is the only force which is preventing that motion. That's one. If you take the moment around this, put a joint over here. These guys are not making any motion for it, because all of these three are crossing this point. But this guy is starting to rotate this guy. How? Clockwise. This is the only force which is preventing that motion. We are in a steady equilibrium condition, then this guy should be this. Right now I have two like these ones. Pulling this structure to the left. These guys are not contributing in that direction. This is the only force which is preventing that motion, meaning that this should be like this. This is the way that I'm finding the correct directions, and by having the correct directions you can find the positive results. This is one thing to discuss. The other thing is that they are asking you that are these links in tension or compression, and that's the question over here. And the thing is that you need to consider the free body diagram of the links. Let's get back to the links and put them here. I have F and E. What is this force? This force is the force that link FE is applying on the pin E. Because of the Newton's second law, we know that the reaction of this would be applied on the link. And what is the reaction? The reaction is exactly the same force but with reverse direction, meaning that this is F, E, F. And for preventing the motion of this guy, we need to put another force, F, E, F. And this means this guy is under tension. Okay, the same story here. However, here what is happening there is like this. If I put F, B, C over here, I have B and C over here, and I'm putting the reactions over. This is the same force with reverse direction, and as you can see, this is under compression. This is the way that you do that. Then we consider the free body diagrams like C and F, and look at the forces which is applied on the pin. This is the force which is applied on the pin. The reaction of that would be applied on the link. And you put the reactions with reverse directions, the same magnitude, and this is tension, and this is compression. Okay, that's it for this video, and in next videos I will try to show you some more examples of the trusses and how to deal with different kind of problems. Thank you.